Hello again, this is Jeffrey Fox, and we're continuing our discussion of recommender systems with a short discussion of item-based collaborative filtering. As always, we're using clouds, we're running data analytics and collaborative filtering, and the k-nearest neighbor algorithm are just a very good example of the algorithms of data analytics. We're doing it collaboratively, processing big data. We saw previously how much data Amazon, eBay, Netflix, etc. have on rankings, and we're solving problems in X Informatics. And those are all the values of X. So previously, we discussed collaborative filtering in the case of users, and that could often be applied in real time to find the users that are near each other, and that's why it's called memory-based. And it's hard to do that for very large problems because of the large number of customers, and the customers live in the space of items, and there are also a lot of items, of course. Another set of approaches are called model-based approaches, and these correspond to either offline or sometimes you might call them batch. You make some sort of model or picture of the world, and you determine its parameters by running it once and for all, maybe overnight or every week or something like that. And at runtime, you do something simple, which sometimes is called interpolation, and you take a model you've already determined and use it to make predictions. And then you either redo the model from scratch, or often these models can be updated iteratively with a clever algorithm. And the actual model building is quite computationally intense, but the update or the prediction stage is not terribly computationally intensive. And here we'll look at item-based collaborative filtering, which is an example of such a model-based approach. In the user-based collaborative filtering, you took a set of users. Users were points in a space of items, and you use that to make predictions. Now we're looking at items, and items live in a space of users, and we're trying to find items that are similar to each other, and so we can use them to make predictions. Here is a simple example. We have our usual shopper, Alice, and she is looking at a set of items. She's ranked 4 of them, items 1 through 4, and we're trying to decide whether item 5 is good for her. And we have other information, of course, enormous amounts of other information. In particular, we're interested in users who've actually ranked the same items that Alice has. And we want to use those rankings to identify an estimate for the Alice's ranking for item 5. And so it's these rankings of user 1 through user 4 that we need to somehow average or in a creative fashion to find Alice's ranking. And we can do that by finding items that are near item 5 and use then the ranking of Alice for those items which are near item 5 to predict her ranking for item 5. So those are those rankings, 5 for item 1 and 4 from item 4, and we'll use that to make an estimate for item 5. So, as always, we explained that these items live in a space of users. It's a slightly funny space in that the items are only ranked by a few users, and therefore in calculating distances in this space, although it looks like a normal space, it isn't really, because only a few of the components are known. So the components in this space are the rankings. That's true in both item-based and user-based. The only issue is whether we think of users in the space of a space where the dimensions are items, or items in the space where the dimensions are users. So we have vectors in this m-dimensional space where m is the number of users, and we can calculate the similarity in many ways. There is and the simplest form is the normal form you'd actually use in a Euclidean space, which is just the scalar product of two vectors. Each of these vectors is an item, and then you take the scalar product and divide by the modulus. And because of the many missing components, this is not entirely unambiguous. And so we had used this adjusted cosine similarity, which has been experimentally shown to be effective, and that does some adjustment. It takes out the fact we've already discussed that you need to take out average values because certain users are very grumpy and they always rank things low, and those tend to distort results. So in order to calculate the similarity in between A and B, you find all the users who've rated both A and B. You then calculate the scalar product at the top, which is the sum of these users in common between A and B, of the ranking of a user for A times the ranking of user for B, subtracting in each time the mean value. Overall, this mean is the mean for a particular user over all items. And then you divide it by the corresponding distances. And remember, these distances, which are slightly special because they're not the normal distance, because this is not the sum of the distances, the ranking squared for item A over all users. It's just summed over the users in common between A and B. So the length of A in this formula in the middle actually depends on B, because it only uses users in common. So we just want, when we calculate this length A down here, we only calculate it in the sum of the users in the space set big U, and big U depends on both A and B. So this makes it a little different from normal scalar products and normal intuition. So when we are looking at the length of A in this formula here in the middle, then we normally length of A is something that only depends on A. However, because we're only summing over the users in common between A and B, then it actually, the length of A depends on B. And so that's exhibited in this formula here. So this length formula has two features of importance. Only sums over the users who are both ranked A and B, and it subtracts the average ranking of each user. Once we've determined this, we now have to predict what Alice will think of a particular item. And so we have the sum here of over the people who've ranked. These are the users who have rated an item I. And then we have the similarity between I and the thing we're trying to predict times the rating of this user for I. And then we divide it by the sum of those similarities without the rating. And then we only do this over a neighborhood size. And that's where the nearest neighbor comes in. And again, this is not something I'm very familiar with. And it obviously will depend on the size of the data set and possibly even the type of data set. And I'm sure that all the major companies have this as part of proprietary corporate folklore. But some number here is suggested from 20 to 50. But that's 2002, and an awful lot has been learned since 2002. So I think that's has to be determined.